In this video, we will talk about signals. This is the model that we will work with. You can see on the left the transmitter. On the right is the receiver. And between the two of them is the channel. What the transmitter transmits and the receiver receives is the signal. In this video, we will focus on the signal. A definition of the signal could be a function that describes a physical phenomenon, and we use it to carry information. A good example is the voice, and also the output of a sensor. There are two domains to work with signals. The first one is the time domain. Here we will follow a time perspective. This is the most common approach and the easiest way to think about the world, with a time perspective. But there is also a very useful domain that is the frequency domain, where you will have to follow a frequency perspective. To go from one domain to the other, we will use a mathematical tool called transform. In the time domain analysis, we will use some parameters to characterize the signals like amplitude, the period, if the signal is periodic, power, root mean square, and some more. Here we can see two examples of signals. T is the period of the signal. XP is the peak of the signal, the maximum value of the signal. We'll also need to deal with the mean value, the average value of the signal, which follows the expression that you have in the middle of the slide. Also, it's very important to know the root mean square value of the signal. And also, a very, very important parameter, it's the power. Here are two good examples of signals. The first one, it's a sinusoidal signal, a cosine or a sine signal, where you can see all the previous parameters, the peak, the RMS, the power, etc. And also the triangular signal. You need to see that the parameters change from one signal to the other. Later on, we will focus on some properties of the signals, so you will have time enough to learn more about it. In the frequency domain, we use other parameters like bandwidth, a very, very popular term and here we will learn about it in a better way. Also the power spectral density and, as in time domain, the power. For example, let's consider the signal that you have in the left, a square signal. If we transform this signal from the time domain to the frequency domain, we obtain the signal on the right. It's a sync signal. Here, you only need to realize that there are two domains, and one domain is very different from the other. The shape of the signal on the time domain is very, very different from the frequency domain. Below, you have the most common notation for these two domains. Lowercase is used for time domain signals, and uppercase is used for frequency domain. Something important is that we also call the frequency domain spectrum. The next important concept in this video is the bandwidth. You may probably have heard about it. What's the bandwidth? The bandwidth has a lot of different definitions, but all of them point to the same concept. It's a range of frequencies that contain something significant about the signal. For example, the power. Some people define the bandwidth as the entire range of frequencies that contain all the power of the signal, but this definition sometimes it's a little bit impractical. So most of the time is defined as the 3 dB bandwidth. 3 dB, as you will learn very soon, means the half of the power. So The 3 dB definition of bandwidth is that band whose width it contains the half of the power of the signal. But there are so many different definitions. Finally, the last important concept in this video is the logarithmic units. It's a very useful tool in communications because in communications we deal with very large numbers and also very small ones. Let's look at an example. Imagine that you are designing a mobile network. The transmitter has a lot of power, let's say 20 watts. But the receiver, due to the attenuations and some other phenomenon that we will learn about later, attenuates this signal. So in the receiver, you will only have a very, very short part of this signal. Almost all the power of the signal will be lost. We will not reach the receiver. So what we do here to work with these different numbers is to work with a logarithmic unit. This logarithmic unit, you may have heard about it. It's the decibel. The decibel relates these two magnitudes in the way that you have at the top. We calculate the ratio between these two magnitudes. We take the logarithm, the decimal logarithm, and also we multiply the result by a constant. So you have there an example. 20 watts divided between 1 trillionth of a watt, it's 20 trillion times bigger the transmitted signal than the received signal. If we take a logarithmic unit, we can say that the difference between one signal and the other is 133 dBs. It's very much easier to handle 133 dBs than the other quantity. Also, we can take logarithmic units to represent absolute magnitudes, not only relative magnitudes as before, but also absolute magnitudes. For example, the received power, 1 trillionth of a watt. We can say that it is minus 90 dBms. This is an absolute power. So to sum up, we have two new units. The decibel, that's a dimensional, and we use it to relate to magnitudes, and also the dBm, which is a power unit, an absolute measurement. All of this leads to something very useful that I mentioned before when I was defining the bandwidth, that 3 dBs means the half of the power. If you take a very simple operation, 10 decimal logarithm of 3, you will find out that it is more or less 3. So here we are. Thank you very much for your attention.